in PSN College of Engineering and Technology. In our previous videos, we just find the diagonalization of a matrix. Regarding matrix, we just calculated all those things. In that continuity, I am going to give a quadratic forms contents. This video contains what are the contents in the sense quadratic forms and the symmetric matrix. Next, orthogonal reduction of a quadratic form to its canonical form. How we are reducing a quadratic form to the canonical or a canonical to the quadratic. Next, rank, index, signature and nature of a quadratic form. How to calculate from a given matrix. And some examples and some practical problems and MCQs for your reference. Okay. Now, let's enter into the topic. First one, quadratic form. What is meant by quadratic form means? The definition is a homogeneous polynomial of second degree in any number of variables is called as a quadratic form. The main thing is the polynomial should be homogeneous and the degree should be 2. For an example, we are just giving it 3 examples for your reference. First one is ax square plus by square plus cz square is one of the quadratic form in 3 variables x, y, z. Here x square, y square, z square. All are having a degree 2 and each is a homogeneous polynomial. Suppose if we have not necessary for x square, y square alone, they may also be written as x, y, y, z, etc. For the time just giving you the second example. Ax square plus by square plus cz square plus 2hxy, 2gyz and 2fzx is again a quadratic form in 3 variables x, y, and z. Each and every term have a degree 2. Same way, ax square plus by square 2hxy is again a quadratic form in 2 random variables. These are the examples for the quadratic form and this is the definition for the quadratic forms. Next, I am just giving you the general definition for a quadratic form. If our quadratic form having a n variables, then what is the form in a sense? Summation j varies from 1 to n and summation I varies from 1 to n, bij into xi xj. This is the general format for our quadratic form. Next, for a quadratic form, how we can reduce our quadratic form into a symmetric matrix. In this section, we are going to see this. First one, let summation j varies from 1 to n and I varies from 1 to n. Bij xi xj with the quadratic form in x1 to xn. It means for n variables, the general quadratic form is this thing. Now I am defining aij such a way that nothing but half times bij plus bji. Then we have aij is equivalent to aji. We can write bij xi xj plus bji xi xj can be written as aij plus 2 aji into xi xj. Therefore, we can rewrite the quadratic form as instead of bij, we can replace by aij. That is, summation I varies from 1 to n and j varies from 1 to n. Bij xi xj can be written as summation j equal to 1 to n and summation I is equal to 1 to n aij into xi xj. Here A is nothing but a matrix of a symmetric matrix having elements as aij, where I varies from 1 to n and j varies from 1 to n. Let capital X denotes the variables of x1 to xn. Then x transpose takes the value as we have to change the rows into columns. So x1, x2, xn, xn. Now x transpose ax can be calculated as summation j equal to 1 to n, I equal to 1 to n, aij into xi xj, which is equivalent to summation bij xi xj. So which is the given quadratic form. Therefore, we can write the given quadratic form summation of bij xi xj as x transpose ax, where aij takes the value of half times bij plus bji and capital A denotes the symmetric matrix. Thus, we can associate a symmetric matrix A with the given quadratic form. Remark in the sense, how we are going to construct a matrix. In general, given a quadratic form in n variables, then the associated symmetric matrix is constructed by 2 ways. First, we have to construct the diagonal elements. Second, we have to consider the remaining elements, that is non-diagonal elements. The first step is how we are considering the diagonal elements in the sense Aij takes the value of coefficient of Axi square, and the non-diagonal elements takes the value as, it means for I not equal to j, both Aij or Aji takes the value as half times coefficient of Xi Xj. In this way, we can convert our given quadratic form to a symmetric matrix. I am just giving the examples. Example number 1. Write down the matrix of the following quadratic forms. Ax1 square plus bx2 square plus 2h into x1 x2. They have given a quadratic form, so each and everything has a order 2. Yes. First let x takes the value of x1 and x2. Then the given form is of the two variable having x1 and x2. Let us consider the matrix capital A, which takes the value of a11, a12, a21 and a22. Since x takes two variable, we are taking our symmetric matrix in the order of 2 by 2 matrix. We take a11 as coefficient of x1 square and a22 as coefficient of x2 square. And a12 and a21 takes the value of coefficient of x1 x2 by 2. Thus, we have A is equal to A, H, H, B, which is the associated symmetric matrix. From the given expression, x1 square coefficient is A. Thus, the matrix reduced to A, H, H, B. Again, one more example. Second one, 2x square plus 3y square plus 6xy. Then the associated symmetric matrix is given as 2, 3. First, we have to fix the diagonal elements. X square takes the value of a11, y square takes the value of a22, and the xy value and yx value divided by 2 takes in the position of a12 and a21. Thus, the matrix takes the value of 2, 3, 3, 3. Next, third example. Suppose our matrix containing 3 variables, 2x square plus 5y square minus 6z square minus 2xy minus yz plus etc. Then we have to find the matrix. In that associated symmetric matrix, our matrix consists of a 3 by 3 order. First, we have to fix the diagonal elements. 2, 5 and minus 6 is fixed in the diagonal. Then remaining elements we have to divide by 2. In the position of xy or yx, we have to put minus 2 by 2, which is nothing but minus 1. So, a12 and a21 takes the value of minus 1. And in the position of zx or xz, it means a13 or a31 takes 8 by 2, which is nothing but 4 value. And in the position of yz, it means in the position of a23 or a32. We have to put coefficient of yz by 2, which is nothing but minus 1 by 2. Thus, our matrix becomes in the format. In this way, we can convert our given quadratic form into a symmetric matrix. Similarly, one more example, having a number of variables as 4, then the associated matrix is calculated in this way. Here, first thing, we have to fix the diagonal elements, and then we have to fix the remaining non-diagonal elements by divided by 2. The coefficient is going to divided by 2. Next, how we are going to form a symmetric matrix to a quadratic form. If they are given a matrix, then how we are converting it into a quadratic form in this section. Yes, first one. Suppose if we are given a symmetric matrix of size n, then we will reduce the quadratic form in n variables as x1, x2, etc., xn as follows. Let us take capital X is equal to x1, x2, etc., xn. Then calculate x transpose A into x, which is nothing but summation Aij into xi xj, nothing but same thing as summation of Bij into xi xj, which is a quadratic form. Here the coefficient of Bii of xi square is nothing but Aii for I equal to 1 to n. And for I not equal to 1, the coefficient of Bij of xi xj as 2 times Aij. Thus, the quadratic form given by the symmetric matrix can be written as a11 into x1 square, a22 into x2 square, etc. Ann into xn square plus 2 times A12 into x1 x2, 2 times A13 into x1 x3, etc. plus 2 times an minus 1 into n, xn minus 1 into xn, in this format. Yes, one can check the following, which means there is a one-to-one correspondence between the set of all symmetric matrix of size n and the set of all quadratic forms of the n variables. Okay. These are some of the examples I am just giving you. First one, write down the quadratic form corresponding to the following symmetric matrix. Let us consider the matrix A is equal to this thing. Solution. A is a 3 by 3 matrix. Okay, so we need to 3 variables, named it as an x1, x2, x3, randomly chosen. Now let us find it. Capital X is equal to x1, x2, etc. The required quadratic form is given by x transpose Ax, which is nothing but x1, x2, x3 into the given matrix A into x. On multiplying this, we just obtain 2 into x1 square plus 3 into x2 square plus 1 into x3 square plus 8 into x1 x2 plus 10 into x1 x3 plus 2 into x2 x3. It means from the given matrix alone, we just able to write the quadratic form. How in the sense? By taking the diagonal elements into square values. It means 2 into x1 square, 3 into 1 into. And the remaining we have to multiply by 2 and put the coefficients. Yes. Next thing. Suppose if the given matrix is in the order 4 by 4, then we have to consider the variable as x1, x2, x3, x4. We can find the value and the quadratic form can be obtained by putting diagonal elements. First of all, the coefficient 1, minus 4, 6 and 2 as taken as a coefficient for x1 square, x2 square, x3 square and x4 square, and the remaining value, for the remaining value we have to multiply by 2 and we have to put in the coefficients in the place of x1, x2, x1, x3, x1, x4. Similarly, 2, 1, 3, 2, etc. Thus, we obtain the quadratic form as x transpose Ax is equal to x1 square minus 4x2 square, etc. in this way. Thus, we can obtain a matrix to a quadratic form. In the same way, if they have given a quadratic form, we can reduce into the matrix, and also if they are given the matrix, we can reduce into the quadratic form. Vice versa, we can find the value. Next, reduction of the quadratic form to its canonical form or sum of square forms. Next section, we are going to reduce our quadratic form to a canonical form. Okay. Let us consider our x is equal to x1, x2, etc. of n variables and capital A as a symmetric matrix. Then the quadratic form is given by x transpose Ax is equal to summation I equal to and summation j equal to Aij into xi xa. Let lambda 1 to lambda n be the eigenvalues of capital A and x1, x2, etc. xn be the corresponding eigenvectors for the given matrix A. And assume that our x1, x2, etc. xn are pairwise orthogonal and modulus of xi is equal to 1. Since A is a symmetric matrix, we know how to find the diagonalization of a matrix by using our orthogonal transformation. We can find the diagonal matrix in this way, that P transpose AP is calculated as D, where D is nothing but the lambda 1, lambda 2, etc. in the diagonals, and all other elements are 0, which is nothing but the diagonal matrix, whose diagonal elements takes the value of eigenvalue of the given matrix A. Thus, P transpose AP equal to D implies the given matrix A can be written as P into D into P transpose. Here, P is nothing but orthogonal, so that we can take P inverse as P transpose. Now, we can write the given quadratic form as x transpose Ax is nothing but x transpose PD P transpose x, where first two values can be taken as P transpose x the whole transpose D and P transpose into x. Let us assume that the new variable y and replace x P transpose as y. Thus, the above equation now reduced to x transpose Ax can be written as y transpose D into y, where D is nothing but the diagonal matrix. On multiplying those values, we just get lambda 1 into y1 square plus lambda 2 into y2 square plus etc. lambda n into yn square, which is the canonical form or sum of a square form of the given quadratic form. Thus, we reduce our given quadratic form to the canonical form. This is the procedure for how we are converting our quadratic to canonical form. The procedure is nothing but given is in a quadratic form, we have to convert the given quadratic form into the symmetric matrix first of all. Then we have to reduce our given matrix A by through an orthogonal transformation, and we have to find the value by using the diagonal matrix B. After finding the diagonal matrix B, again we have to replace that diagonal symmetric matrix to a canonical form. Hence, here we take Y as P transpose X, where P is orthogonal matrix with P transpose AP takes as D. This is the procedure for orthogonal reduction of a quadratic form to its canonical form. Now, I am just giving you some of the examples to identify how to reduce our quadratic to the canonical. First one, in which it carries two more sections. It means on reducing the quadratic form to canonical, sometimes we have a repeated eigenvalue, sometimes we have a distinct eigenvalues. So, it belongs to two cases. For distinct, it may be little bit easy. For repeated eigenvalues, we have to go in some little bit changes in that. First case, I am just going to produce the distinct eigenvalues. It means all the eigenvalues of the given matrix are distinct. Problem number 3. Reduce the quadratic form given they have given one expression into the canonical form using an orthogonal transformation. First one, I am just reducing my quadratic form to the symmetric matrix. First step, and naming it as A by taking x square, y square, z square coefficient in the diagonals and the remaining values by 2. Thus, our A is reduced to 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. Next, the characteristic equation of A is given by, on solving, next our value is nothing but, what is the first step? We just reduce our quadratic to the given symmetric matrix. Next, we have to find the symmetric matrix to the diagonal matrix. We have to convert the matrix to the diagonal form. With the procedure, first procedure is we have to find the eigenvalue and eigenvector. According to the eigenvalue, we have to move next. To find the eigenvalue, I am just finding the first characteristic equation. Is given by modulus of A minus lambda I equal to 0. Thus, I am taking the modulus value of A minus lambda I. We have an equation in a quadratic, in a cubic equation, lambda cube minus 18 lambda square plus 45 lambda equal to 0, which is nothing but the characteristic equation of the given matrix A. On solving this cubic equation, we just get an eigenvalue as 0, 3, 15. Note, all the eigenvalues of A are here are distinct. It means just of 0, 3, 15. All the three eigenvalues are distinct. Okay. Since all the eigenvalues are distinct, the eigenvectors are pairwise orthogonal. It is very much clear. So, find the eigenvalue. For each eigenvalue, we are going to find the eigenvectors of A. Let capital X is equal to x1, x2, etc. be an eigenvector corresponding to the eigenvalue lambda. Then x satisfies the equation as Ax equal to lambda x or A minus lambda into x equal to 0. On equating the equation, we have three equations 2, 3 and 4. On multiplying those values, and it is written in an equation format as 2, 3 and 4. This is a general form. On replacing our lambda as our eigenvalue, we get a solution. Yes. First case 1. If our lambda takes 0 in the above equation, we have our equation 2, 3 and 4 reduced to equation 5, 6, 7. I am just replacing my lambda as 0. Next, on solving 5, 6, 7, we can take any two, either 5, 6 or 5, 7 or 6, 7. On solving the above equation, we have three equations, 3 and also it can be randomly chosen. We can choose any two equation and we can solve and find the solution. On finding the solution, we just getting an answer as x1 equal to 1, x2 equal to 2, x3 equal to 2. Thus, we have x1 dash is nothing but 1, 2, 2. Next, we have to find the modulus of x1 dash, which is nothing but a root of sum of square of each coefficients, which is nothing but root of 1 plus 4 plus 4, nothing but 3. Therefore, capital X1 is written as 1 by root 3, 2 by root 2 by 3 and 2 by 3. This is our first model eigenvector. Next, for same value, for 0 we just calculated. For next eigenvalue, take lambda equal to 3, the next one, and substitute in equation 1. Thus, we get our equation 2, 3 and 4 now reduced to 8, 9 and 10 by replacing lambda equal to 3. On solving any two equations, here too, the three equations, 3 unknowns, it can be easily solved on taking any two equations randomly chosen, or 8 and 9 or 9 and 10 or 8 and 10 as our equation. On solving any two equation, we get the answer as an x1 equal to 2, x2 equal to 1, x3 equal to minus 2. By taking x2 dash as 2, 1 minus 2, we have to find the same thing, modulus of x2 dash, then x2. Therefore, capital X2 is nothing but x2 dash by x2 modulus of x2 dash, which is nothing but 2 by 3, 1 by 3 and minus 2 by 3. In the same way, by taking lambda equal to 15, the equation number 2, 3 and 4 reduced to 11, 12 and 13. On further solving equation number 12 and 13 or 11 and 12 or 11 and 13, we get the answer as 2, minus 2 and 1. Therefore, capital X3 is noted as 2 by 3, minus 2 by 3 and 1 by 3. Thus, the diagonalization of an A by an orthogonal transformation, just we are going to find the value. Since by taking P is equal to x1, x2, etc., that is the model matrix 1 by 3, 2 by 3, etc., all the three. Then P is an orthogonal matrix. P transpose implies that P inverse is nothing but the P transpose. Okay. Now consider P inverse AP, which is nothing but P transpose AP. We already calculated P. So take a transpose, first thing, then A matrix given matrix, then put a P matrix. On multiplying the three matrices, we obtain an equation as, we obtain a matrix as 0, 0, 0, 0, 3, 0, 0, 0, 15, which is nothing but D, which is nothing but the diagonal matrix, whose diagonal elements are nothing but the eigenvalue of the given matrix. Thus, we have diagonalized the matrix A using an orthogonal transformation. Thus, I find the value for a given matrix in terms of diagonal matrix P. Now, we have to reduce this into the canonical form. Okay. The given quadratic form is given by X transpose AP. X transpose AP, then replace our A by P transpose. A is equivalent to this thing, so I am replacing. And taking our capital Y as P transpose into X, we have capital Y is nothing but Y1, Y2, Y3 into P transpose D into capital X. Thus, we have X transpose AX is equal to Y transpose D into Y, which is nothing but Y1, Y2, Y3, 0, 3 diagonal matrix into Y1, Y2, Y3, which is nothing but 0 into Y1 square, 3 into Y2 square plus 15 into Y3 square, where 0, 3 and 15 are nothing but the eigenvalue of the given matrix. Therefore, we have X transpose into AX has only square terms. This is the canonical form of the given quadratic form, where y1 takes the value of x1 by 3 plus 2x2 by 3 and 2x3 by 3. And y2 takes the value of 2x1 by 3, x2 by 3 minus 2x3 by 3. Similarly, y3 takes the value of this thing. In this way, we have converted the given quadratic form into the canonical form. This is one of the example by solving distinct eigenvalues. Next case, suppose our eigenvalues are repeated. Then how we can solve? How we can find? Same thing. Question number 4. Reduce the quadratic form to its canonical form using an orthogonal transformation. On seeing the question itself, we can't find whether it has a repeated eigenvalues or non-repeated eigenvalues. So, by solving, first we have to convert the quadratic form to the canonical form. We have to give the quadratic form to the matrix, first step. Second step, convert the given matrix to the diagonal matrix by orthogonal transformation. In order to find the diagonal matrix, we have to first find the characteristic equation, next eigenvalues, next eigenvectors. According to our eigenvalues, eigenvectors can be calculated in the way that all the three are orthogonal. So, we are using orthogonal transformation to transfer our given matrix to the diagonal matrix. Let's move on to the problem. First one, the symmetric matrix of the quadratic form. Just we reduced the quadratic form to the symmetric matrix as this thing. Next, the characteristic equation is given by modulus of A minus lambda I equal to 0. On solving the given matrix, we just having a cubic equation as lambda cube minus 10 lambda square plus 12 lambda plus 72 equal to 0. On solving the cubic equation, we just obtain the eigenvalue as minus 2, 6 and 6. See, on observing the eigenvalue, we found that the eigenvalues are repeated. As the eigenvalues are repeated, we have to find the eigenvector first for non-repeated eigenvector. For non-eigenvalue in the sense, we can't write 6, 6, 2. First find the value for non-repeated one, which is for minus 2. For minus 2, we just calculated the eigenvector. Next, for 6, we have to calculate the eigenvector. On comparing these two eigenvectors, we are going to calculate the third one. Yes, let's move on to the sum. The eigenvalue for lambda equal to 6 is repeated. Okay, just we have to note that one, which one is a repeated. We have to find the eigenvector for the repeated is in the last. Okay, first we have to find the eigenvector. What is the procedure for that? We know that A minus lambda into capital X equal to 0. Which equation satisfying this condition gives the eigenvector. Thus, the given matrix minus lambda into x1, x2, x3 as this thing. Name it as an equation number 14. On solving this equation, we have 15, 16 and 17. This is a general equation for to find the eigenvector. Okay. On substituting lambda equal to first case of lambda equal to minus 2, our equation 15, 16 and 17 reduced to 18, 19 and 20. In which 3 equations, 3 unknowns. So, we can find the answer. On solving any 2 equation, we get the answer as 1, 0, minus 1. Therefore, capital X1 takes the value of this thing, modulus of X1 takes the value of this thing, and therefore, thus the modal matrix of X1 can be written as 1 divided by root of 1 plus 1, 2, root 2, 0 by root 2, minus 1 by root 2. Okay. Next, for lambda equal to 6, we have to find one thing. Lambda equal to 6, the eigenvector can be calculated, and our equation 13, 14, 15, just 15, 16 and 17, this equation becomes 21, 22 and 23. On solving the 3 equations, we just getting the answer as 1, 0, 1. Next, this is only independent eigenvector corresponding to lambda equal to 6. Next, we have to find another one more eigenvector for lambda equal to 6. For that, we have to take, if x3 satisfies the equation all the 3, then it is orthogonal. In that way, I am going to choose x3 transpose into x2 equal to 0, then x3 transpose into x2, which is nothing but x, y, z into 1, 0, 1, which takes the value of x plus z equal to 0. Same thing, x3 transpose into x1 equal to 0, which takes the answer of x minus z equal to 0. I am just multiplying my x3 with x1 and x2. On equating on the above eigenvector, by using the above eigenvectors, we are going to calculate the third one. To find x3, just we have to solve the equation of x minus z equal to 0 and x plus z equal to 0 simultaneously. Here we get x is 0 and z is equal to 0. And recall as here y is an arbitrary missing. Thus, we can take any value which is nothing but let us assume that it is 1. Therefore, the eigenvector capital X3 can be calculated as a 0, 1, 0, which is a non-zero eigenvector, so this is the answer. And we have to check whether x1 into x2 equal to 0, x2 into x3 equal to 0 and x1 into x3 equal to 0. Here, all the 3 values takes as 0. Therefore, we take our x1, x2, x3 are pairwise orthogonal. Next thing, orthogonal reduction of A. We just calculated the diagonal matrix of the, it means eigenvalue and eigenvector. So next, for orthogonal reduction, we have to calculate the modal matrix. For that, we have calculated x1 by mod x1, x2 by mod x2, x3 by mod x3, which takes the value of first one 1 by root 2, 0, minus 1 by root 2, second one 1 by root 2, 0, 1 by root 2, third one 0, 1, 0. Then P is orthogonal and we have replaced our P transpose as P inverse. Now consider P transpose A into P. On multiplying the 3 equations, we obtain the matrix as minus 2, 0, 0, 0, 6, 0, 0, 0, 6, which is nothing but the diagonal matrix. Thus, we get P transpose AP as D. Therefore, A is nothing but P into D into P transpose. Now, consider our X transpose AX, which can be written as y transpose d into y, where y takes the value of p transpose into x, where p transpose into x is nothing but matrix of multiplication of p transpose into x value. Now we can write the given quadratic form as x transpose ax is nothing but y transpose d into y, where y is nothing but y1, y2, y3, y transpose is in the row matrix and y is in the column matrix. Now just in the middle we just substitute our d value as -2, 0, 0, etc. On multiplying the three matrices, we obtain the equation as -2 into y1 square plus 6 into y2 square plus 6 into y3 square, where the coefficients takes the value as our eigen values. Thus, x transpose ax is this thing, which is nothing but the canonical form of the given quadratic form. Thus, we have x1, x2, x3 is equal to this thing, which implies our x1 takes the value of half into y1 plus y2, x3 takes the value of y3 and x3 takes the value of 1 into this thing, which means thus we have x1, x2, x3 is nothing but p into y matrix. Thus, we calculated our quadratic form to a canonical form. Next, same thing. For non-repeated roots, it is easy to calculate the eigenvector to the diagonal matrix, in which for repeated it is little bit. So, one more I am just giving you, whether the repeated roots may be positive or negative. In this case, just in the previous problem, I just gave you the repeated root as a 6. It means in the positive repeated roots. Now I am just giving the negative repeated roots. Suppose if it happens in a sense, how we can proceed? Problem number 5. Reduce the quadratic form to its canonical form for using the orthogonal transformation. The given symmetric matrix, the given quadratic form is converted to a symmetric matrix. First, convert this into the symmetric matrix and by using the characteristic equation, find the eigenvalues. I am just now converting the matrix and write the characteristic equation. On solving the cubic equation, we obtain the value as -1, -1, 5. This is nothing but the answer for the cubic equation, which is nothing but the characteristic roots or eigenvalue of the matrix or given quadratic form. Next, -1, -1, 5. Here -1 is a repeated. Okay, we have to note that one. Next, find the general form for the eigenvector. Name it as an equation number 24. On solving equation number 24, we just obtained an equation as 25, 26, 27. In this 25, 26, 27, we have to replace our lambda by -1 and 5. First case, we have to put lambda equal to 5. It means for non-repeated roots, we have to substitute and find x1. Next, we have moved to the repeated one. For lambda equal to 5, the above three equations are reduced to this thing. On solving the three equations, we obtained our x1 as 1 minus 1 plus 1. In the same way, we have to replace our lambda by -1 and substitute in 24, we get the three equations. On solving the above three equations, we obtain the equation as this thing and find the eigenvector as 1, 1, 0. We now obtained two equations. Third one. To find the third one, we have to multiply that x3 with x1 and x2 equal to 0. Thus, we find the value of x3 as thus we obtain the value of x3 as x3 into x2 equal to x3 transpose into x2 equal to 0. We have x plus y equal to 0. On solving the above two equations, it means x3 transpose into x1 equal to 0. We have one equation, x minus y plus z equal to 0, the above one. First line. Next, x3 transpose into x2 equal to 0 is nothing but x plus y equal to 0. On solving the two equations, we obtain the value for us x3 equal to -1, 1 and 2. Now, I am going to find the diagonal matrix. So, in order to find P. To find P, yes. To find P, let us calculate x1 by mod x1, x2 by mod x2, x3 by mod x3. Thus, modulus of x1 takes value of root 3, root 2 and root 6. Thus, I calculated the modal matrix P. Now, P transpose equal to 1, which implies P transpose is equal to P inverse. Now, consider P transpose AP on multiplying the three matrices. we obtain the matrix as a diagonal one, which is nothing but 5, 0, 0, 0 minus 1, 0, 0, 0 minus 1. Thus, our matrix capital A is equal to P D P transpose. Now, the canonical form. We converted the given quadratic form to a diagonal matrix. Now, we have to convert it to the canonical form. The same procedure as earlier. Our X transpose AX is nothing but P transpose X whole transpose into D into P transpose X, where Y takes the value of P transpose into X, which is nothing but matrix of P transpose into X1, X2, etc. Thus, our matrix X transpose AX takes the value of 5y1 square minus y2 square minus y3 square, which is the canonical form of the given quadratic form, in which our X, our Y, y1, y2, y3 takes the value as 1 by root 3 into x1 minus x2 plus x3, etc., which is nothing but the product of P transpose into X. It means here the original variable x1, x2, x3 is now changed to the new variable y1, y2, y3. In this way, we can convert our quadratic form to a canonical form in both the cases. It means for repeated eigenvalues or for non-repeated eigenvalues, we can be able to convert our quadratic form to a canonical form. Yes, this is one of the section. Next, shall we move on to the next section? How to find the rank, index, signature and nature of the given matrix. Okay. First definition for rank. Let us assume that X transpose AX be the quadratic form. Let us assume the quadratic form. According to the quadratic form, we have to find the rank. Definition number 1, rank. Rank of the quadratic form is calculated as the number of non-zero eigenvalues of the given matrix A. Without eigenvalue, how we can calculate this? The number of non-zero terms in the canonical form. By calculating eigenvalue, we can find the rank, or by calculating the canonical form number of terms, we can find the rank. Thus, the rank can be calculated as number of non-zero eigenvalues or number of non-zero terms in the canonical form. In the same way, index. Index of the quadratic form can be calculated as number of positive terms in the canonical form or number of positive eigenvalues of the given matrix A. Next definition, signature. How we are calculating the signature of the quadratic form. The signature is nothing but the difference between the positive terms and the negative terms in the canonical form. It means number of positive terms minus number of negative terms in the canonical form, or it can be calculated as number of positive eigenvalues or minus number of negative eigenvalues of A. The difference between the positive terms and the number of positive terms and number of negative terms gives the signature of the quadratic form. Next thing is nature. How we can find the nature of the quadratic form? We can define the nature as positive definite if all the eigenvalues of the given matrix A are positive. If all the values are positive and at least one takes the value as 0, we just name it as a positive semi-definite. Second case. If all the values are greater than or equal to 0 and at least one of them is 0. Suppose if all the eigenvalues are negative, we name it as a negative definite. Suppose all are negative and only one thing, at least one of them is equal to 0, we name it as a negative semi-definite, fourth one. Suppose it takes both positive and negative value, then we name it as an indefinite. This is the 5 different cases for the nature. For a quadratic form to define the nature, these are the 5 possible different things. These are some practice problem for which you can practice and we can find the value in the canonical form. First one is a reduction of the quadratic form to the canonical. Second one is to find the rank, index, signature and nature for the given matrix. And for first one also we can find it. Once we have reduced the canonical in the sense, by seeing the canonical we can tell the rank, index and signature and also the nature. Okay. For second problem, I am just giving you the answer. Next, third one, reduce the quadratic form into the canonical form and also find the rank, index, etc. These problems are to solve. Just so on solving this, if you are having any doubt, let me know. Next, multiple choice question for 1 or 2 questions. The quadratic form corresponding to the symmetric matrix 1, 2, 2, minus 1. how we can reduce the given matrix to the quadratic form? The answer is nothing but option B. Okay, next. The matrix of the quadratic form is given by. We have to convert the quadratic form to a matrix. First one is matrix to quadratic, second one is quadratic to matrix. The second one is option is, answer for second option is A. Last one, the nature of the quadratic form is given by. First we have to find the quadratic form to the canonical or find the eigenvalue, and then we have to define the answer. For this one we have an answer as a semi-definite. Yes, that's the section. So in this section we just find quadratic form and how to relate a quadratic form to a matrix, matrix to a quadratic form, and how to find the canonical form from a quadratic form. Next, how to calculate the rank, index and signature and the nature of the quadratic form. Yes, thank you.